Hey, I'm Shannon. This is my genius son, Isaac. Let's not do the Neutron.
Got schooled up. So we'll be doing neutron stars today, plus one of the people that I go to school with requested that I define plasmonic metamaterials. Okay. So the plasmonic means the interaction with electricity. So to use a physics term, you could say permissivity. And metamaterials are simply man-made. So it's a material that interacts with electric fields. It's actually pretty simple.
Yeah.
But neutron stars. So I've actually done projects on these in my free time. An overview, they're usually about the size of, I've got to define it first. A neutron star is a star in space comprised entirely of neutrons with a few protons, and neutrons make up atoms and whatnot, and protons are in the nucleus of an atom, which is a center for anyway.
And where do neutron stars originate?
They come from the explosions of supermassive stars.
That were not massive enough to become black holes.
Yes, and the star has to be 8 through 25 solar masses. One solar mass is the size of our star, the sun. Okay. But they are made entirely of neutrons, and they spin extremely fast. Scientists actually call them the most accurate clock in the universe because their rotation period for their spin is the same each time, down to the picoseconds sometimes.
And that's not the spin time of every pulsar is not the same. Every pulsar has a different spin time, but to each pulsar, the spin time remains the same and consistent. They're considered the most accurate clock in the universe.
Okay.
Once you learn the spin time on each individual pulsar.
But these loose protons combined with about 100 revolutions a second, combined with a city-sized, super dense hunk of metal, creates an enormous magnetic field. Gauss, G-A-U-S-S, is a measurement of magnetic fields. 1 Gauss is the equivalent to Earth's magnetic field. A neutron star has a Gauss of 1 trillion. Scientists have not been able to replicate that. Their machinery simply falls apart. Okay, so there are 2 types. There are pulsars and magnetars. Which one do you want to do first?
Let's do pulsars.
Pulsars are the more common neutron stars. Those are the ones with a trillion Gauss.
They said a trillion Gauss.
Okay, so
that's a lot.
At their poles, their magnetic poles, north and south, they emit radiation of every electromagnetic frequency. Electromagnetic is any wave that can travel through space. That's including light, radio waves, and anything like that. But sound, sound is a vibration of particles, so it can't travel through space, therefore is not an electromagnetic wave.
Interesting point.
But it's made mostly of X-ray and gamma ray radiation, and actually after X-rays decay, they emit Z-rays. You know that?
No. Sure did.
Okay. Anything else about pulsars you don't have?
No.
So on magnetars?
Sure.
Okay. If you have any input, you can share those. Okay. So a magnetar actually has 1 quadrillion Gauss. So it's
Quadrillion Gauss.
So it's billion, trillion, quadrillion, quintillion, sextillion, septillion, octillion, nonillion, and then decillion.
How many zeros are in quadrillion?
There are 12 in trillion, so there should be 15 zeros in quadrillion.
That's a lot.
How do you keep doing this?
No, I was doing this. I just think.
Monster, scary monster. Okay, so the thing that I find most fun about these is if you get too close to them, they will rip the iron out of your blood and dissolve your cells themselves.
Any material becomes magnetic if you have a strong enough magnetic field. It will rip every molecule in your body apart.
Much like any normal source of radiation that's powerful enough, gamma ray radiation is actually hundreds of times brighter than the light that we can perceive, but it's extremely harmful, the most harmful one. Actually,
What?
there are glitches in the spin of magnetars and pulsars. By a glitch, I mean there are multiple layers of the neutron star, and a glitch is when the inside spins faster than the outside, and an anti-glitch is when the inside spins slower than the outside.
And how can we tell that there's a glitch?
Actually, no. You want to come up with a theory?
I've never heard of a glitch.
Yeah, anti-glitch actually sounds pretty cool.
Anti-glitch and then glitch?
Yeah, anti is slower than. Okay, there are actually some layers. I haven't had these memorized yet. The first layer, the outermost, is magnetic field, and then it has they actually have an atmosphere, but it's very, very thin.
What is sort of interesting is, correct me if I'm wrong, but if you hear about the magnetic field being so much stronger, quadrillion times that of the Earth, that would be scary to a lot of people, but if you're as far as the Earth, let's say Earth is orbiting this, let's say our star was a magnetar, we would not be affected by the magnetic field. The magnetic field is going to be considerably short, considering the size of the star, right?
Okay, so you want to break that down a little bit more? That's kind of...
The magnetic field that they're speaking of, we won't worry about that. Internet connection. Keep the video going.
I was trying to find the strongest magnetic field ever replicated by mankind. But go on.
The cool thing about it is the magnetic field, the really deadly magnetic field that you're talking about around a magnetar is only going to extend about 1 million miles, right?
Yes.
That's like Earth's atmosphere, for a star.
You had a question?
I have a question.
So we were reporting at McDonald's. An employee has a question for us.
What would happen if the magnetic field increased at least 30% every year?
I don't see a plausible explanation as to why that would happen, but if it did happen, then assuming the life of any normal star, it would extend maybe...
That would be in multiples. That would be, what's the word for it? It would be exponential.
Can't get you in the shot.
I mean...
Yeah, exponential, because when you use percentages, it's exponential. Say you get 1% of what you have, and then what you have increases by the greater stock, so then 1% becomes larger.
See you, man. Talk to you later.
That's why it's exponential, if you learn about exponential growth and decay.
I see. Thank you. Come see me if you need anything.
Okay. Thank you.
I can't tell if I'm in the shot right. I'm in the shot right?
Yep. We're still good.
So I haven't been able to find the strongest field ever made by mankind, but circuits are made of metal, and they need circuits to make a magnetic field, so it will rip apart the laboratory if we make it too powerful. They are the densest objects in the known universe, and they're so dense that a single teaspoon would weigh 1 billion tons.
About the same as Mount Everest.
Any input?
I just gave input.
Okay. You want to play like that?
A teaspoon.
Okay.
Weighs the same as Mount Everest.
So back on topic. The outer layer is the magnetic field, and they have an extremely
What would
thin
happen
atmosphere.
if you actually happen to have a teaspoon of it and drop it on the surface?
That would literally create... It might split about half the Earth in half.
I don't think it would split the Earth.
It would sink through the Earth.
Yeah, it would sink. It would sink through the Earth, like the Earth wasn't there.
All the way down to the core.
Right.